The question is, consider three planes in R3. X plus y is equal to 1, y plus z is equal to 0, and x plus cz is equal to 1. For some c in R, for which values of c do these planes intersect in a point? For which values do they intersect in a line? Well, whatever points are in all three of those planes, so in the intersection of the planes, they'll satisfy all three equations. So what we need to do is solve those three equations, and we can do that by doing it with matrices. So let's see, 1x plus 1y plus 0z's is 1. No x's plus 1y plus 1z is 0. 1x plus no y's plus cz's is 1. And our aim is to row reduce that to get as close to the identity as possible. And at the end, hopefully, the value, something about C will tell us what kinds of solutions we can get. So let's see. We want a 1 here, and there already is a 1 there. So that's good. And we need zeros below it. So we already have a 0 below it, and we want a 0 in that bottom row. So we want to do row 3 becomes row 3 minus row 1, because that would give me a 0 in that spot. So 1, 1, 0, 1. Haven't changed this one. So row 3 becomes row 3 minus row 1. So 1 minus 1 is 0. 0 minus 1 is minus 1. C minus 0 is C. 1 minus 1 is 0. So next we want to put, let's see, we've already got an entire column that looks like the identity, so we go to the next column and the next row as well, and we go along row 2 and we find there's a non-zero entry there. We want that to be a 1. And so it already is a 1, and we want zeros above and below. So we want to do row 1 is replaced by row 1 minus row 2. And row 3 should be replaced by row 3 plus row 2, because that would cancel it out to give me a 0. So we haven't changed row 2, so let's leave that as it is. We replace row 1 by row 1 minus row 2. So 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 1 is minus 1, and 1 minus 0 is 1. Row 3 we replace by row 3 plus row 2. So 0 plus 0 is 0, minus 1 plus 1 is 0, C plus 1 is C plus 1, and 0 plus 0 is 0. And then next what we would do is we've got two columns of the identity. We'd go along to the next one, and we'd go down one row, and we find that the first non-zero entry in row 3 is C plus 1. And then we divide by that to get a 1, and then we'd subtract multiples of that row from the other two to get zeros above, and that would give us all our solutions. But if C plus 1 is 0, we're not going to be able to do that. We'll have a whole row of zeros. So that's going to be when we get various different values of C for different numbers of solutions. So if C plus 1 was 0, I could finish the question. I could completely solve it and get x1 equals something, x2 equals something, x3 equals something. So I'd get a unique solution, which would be exactly 1 point. So unique solution when C plus 1 is not equal to 0, that is C is not equal to 1, minus 1, sorry. So therefore planes meet in a point when C is not equal to minus 1. Okay, because we were asked to say when do the planes meet in a point for what values of C, which we have said. That's good. Now, when C is minus 1, we'll get a row of zeros there. which means we'll have a pivot in the first column and a pivot in the second column, but no pivot in the third column, which would make that third column a free variable. It could be whatever we wanted, and once we figured out what it was, we could figure out what the other two were. So a free variables, because I can have whatever I want there, that gives me infinite possibilities. So there's infinitely many solutions. So let's see. One free variable when c is equal to -1. So infinitely many solutions. Okay, so there are different ways to get infinitely many solutions. If you've got three planes, they could all be the same plane, which they're not, or they could meet in a line. So that must be what we've got. So therefore, planes meet in a line when c is equal to -1. And you can find out what that line is by actually solving the equation. And you'd be able to resolve it into point plus t times a vector, and that would be your line. And that is the end of the question.